Today's session is about data structures and algorithm in binary tree concepts. So the recap, we have seen what is an algorithm, its characteristics, introduction to data structure, wherein we saw there are variety of data structures and we saw common data structures like stack, queue, linked list, arrays, then trees, graph. We saw an overview and data structure and its types like primitive and non-primitive, linear and non-linear. And then we saw the types of arrays and one-dimensional array, two-dimensional array, and Java program with the algorithms. So we saw about the simple programs and about the 1D array programs and the 2D array programs. And we saw how list can be implemented using arrays as well as linked list. An array has some limitations which are overcome by linked list. So we saw the linked list definition, its representation, example, and the types of linked list like singly linked list, doubly linked list, circular linked list. And in circular, we had two types like singly circular list and doubly circular list. And we saw the Java program with respect to the single linked list, insertion at the beginning of the linked list and at the end of the list and after the given node. And stack definition, its terminologies, its representation using arrays as well as linked list, its operations like push and pop, its applications like prefix, postfix, infix, arithmetic conversions. And we saw Java programs like stack operations using array, stack operation using linked list. We saw queue, its definition, its example, its terminologies, and its representation using array and linked list. And then binary tree data structure introduction, the general tree format, the binary tree format, and the terminologies and the traversal of binary trees. In traversal, we saw post order, pre-order, in order. And then the queue programs like implementation of queue operation using arrays, its algorithm, Java program to check if queue is full, to check if queue is empty, to check to do NQ and DQ operations, and to have front value, rear value. And then we saw the pros and cons. And in binary tree, we saw the representation of binary trees using arrays as well as linked list. And then in elaboration, we will see like representation using arrays and binary search tree. So representation using arrays. So consider the numbering of nodes in the almost binary tree. So if you do a numbering manually from left to right, if the root node is 1 and the left child is number 2 and the right child is number 3, like if humans do numbering like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from left to right, if you do for each level, the numbering is continued for each level from left to right. At any level in the tree, it can be found that if the number of the parent node is n, then its left child will have 2n and the right child will have 2n plus 1. So we can find out the numbers by a formula called left child with 2n formula and right child with 2n plus 1 formula. So on the basis of this numbering, a tree can be represented in an array. So for example, the first level is equal to the root node and we have n is equal to 1. So we set it as n is equal to 1. When we move to the level 2, we have two children, that is B and C, two nodes. They are the children of A. So left child of A is B and right child of A is C. So in order to find the left child position, we have to use the formula 2n. So here n is the value of the parent of the current node. So the current node is B, for which we have to find the value of its position. Its parent node has a position number n, and that has to be substituted here. Parent node of B is A. So A n value is 1. So 2 into 1 is equal to 2. That's how we have formulated 2. And then for C, we are using the formula 2n plus 1 because it is the right child of A. And the n is substituted by 1 because the parent of C is A. A n value is 1. So we knew the n value 2 into 1 plus 1, which is 3. When we move to level 3, we have two children, D and D, F and G. So D is the left child of B, E is the right child of B, F and G, left child of C, and G is the right child of C. So D here is 2n is equal to 2 into 2 is equal to 4. N is substituted by the value 2 because D's parent is B, D's n value is 2, so it is substituted by 2. And if you go to E, right child of B, so the right child formula is 2n plus 1. So 2 into 2 plus 1, which is equal to 5. And if you go to F and G, you can see it is left child of C and right child of C. So 2n is equal to 2 into 3 is equal to 6. So 2n plus 1 equal to 2 into 3 plus 1 is equal to 7. Here n is substituted by 3 because the parent of F is C. So C n value is 3. So 2 into 3 is equal to 6. Again, here n is substituted by 3 because parent of G is C. C n value is 3. So 2 into 3 plus 1 is equal to 7. Finally, we have H and I and then J. So H, left child of D, which is 2 into n, 2 into 4 is equal to A. I is right child of D. So D's value is 4. So 2 into 4 plus 1, which is 8 plus 1, 9. And then if you see J, J is the left child of E. So which is 2n, 2 into 5 is equal to 10. So this is how we found the values of each node and which is stored in the corresponding position. So if you see A is stored in the index 1. So A is stored in the index 1. So at the index 1, A value is stored. And if you see B, B is stored at 2. And if you see C, C is stored at 3. So A's left child is 2 into n, that is 2 into 1, which is 2. So you can find B. So A's left child is B. Again, A's right child, 2 into n plus 1. So 2 into n is 1. So 2 into 1, 1 plus 1, so which is 3. Similarly, you can map everything. For B, we know the left and right child is D and D. So as you can see, D and E. So 2n. So 2 into 2, 4. So at the fourth index, you can find D. And 2 into 2 plus 1. So 2 into 2, 4. 4 plus 1, 5. At the fifth index, you can find E, which is D's right child. And then C. For C, it is F and G. So this is 3. C's n is 3. So in order to find its children, it is 2n. So 2 into 3, 6. If you go to the index 6, you can find the left child of C, that is F. And then if you want the right child of C, then you have to do the formula 2n plus 1. So 2 into 3 plus 1, which is 6 plus 1, 7. At 7th position, you can find G. So in the tree format, F and G are the children. In the array also, you can find it easily. And if you move on to D, you want to know D's children. So D is H and I. We can check if it is correctly formulated. So 2n. So 2 into 4, which is 8. So at 8, you can find H, the left child of D. And to find the right child of D, the formula is 2n plus 1. So 2 into 4 plus 1, which is 8 plus 1, 9. At the 9th index, you can find I, which is the right child of D. And if you see E, left child J, so the formula is 2 into 5 plus 1. Left child. So 2 into 5, so only 10. Now, if you want to check whether there is any other value, check whether F has any children. So 2 into 6, 12. We don't have anything, right? So this way you can find that our tree is perfectly mapped here. Perfectly mapped. No other doubts.
Can you go back to the previous slide once?